Hi guys, I'm back to talk more about soil, and now we're moving on to chapter 6, and we're going to talk about the information about kind of soil water on a more watershed scale. So last chapter, chapter 5, was about kind of soil and how it moves around on a more microscopic level, how it's attracted to soil particles, how it's influenced by gravity and other water molecules, solutes, and therefore is moving around in those small pore spaces in the soil. And now we're going to kind of take a more macroscopic approach, kind of view of the entire watershed, the area that drains after a storm. And we're going to kind of think about how soil water might be moving around or influenced on that scale. So that's chapter 6. If you're following along with the textbook, basically, we're going to focus on the first few sections of chapter 6 in the 4th edition. These would be section 6.1, the global hydrologic cycle, 6.2, the fate of incoming water, 6.3, the soil plant atmospheric continuum, 6.4, control of ET, which stands for evapotranspiration, 6.5, liquid losses from water in the soil, 6.6, percolation in groundwater. And then we're not going to really address the last few sections of the chapter, which are about enhancing soil drainage. So things like adding drainage tiles and whatnot, septic tanks and drain systems, and irrigation principles and practices. So if those are topics that are interesting to you, relevant to your life, then you may want to check out those sections. But in the interest of time, we're not going to really talk about that material. Okay, so I'm going to share my screen with you, and we'll look at some of the slides, some of these diagrams here. Okay, so soil water on a water cycle or watershed scale. Okay, so first of all, when we're thinking about where is water on the planet, I think probably a lot of you know that most of the water on the planet is in the ocean. About 97% of all the water is stored in the oceans. That's salt water. So that's water that's really not very available when it comes to thinking about agricultural or certainly impacting terrestrial land-based ecosystems. Then of the fresh water that exists in the terrestrial ecosystems, most of that, 77% of that, is stored in ice caps and glaciers. So there's a lot of it in places like Greenland and Antarctica, and also high up in the mountains and other places where there's lots of ice. And that may be trapped there for long periods of time, hundreds of thousands of years. We have ice that's been frozen in Antarctica for over 1 million years in some places. And then the next biggest component of the freshwater is groundwater. So a lot of water exists underneath the ground, and groundwater is actually a little bit different than just soil moisture, which you'll see is also listed on this table here. So groundwater is the water that is kind of farther down in the soil below the water table, which we talked about in the last section. So, right, the water table is this place that is the line between the area that's saturated with soil water below it, and then there's kind of an unsaturated zone above where there might be like capillary movement and whatnot. Okay, so the groundwater is that deeper water, and it often, once the water gets down to that zone, may stay there for up to thousands of years. So that's kind of a long-term storage site. Some of it might be accessed more easily by plants, so it might have a shorter time period of being there, but the groundwater is kind of a more potentially long-term storage site. But that is potentially available to terrestrial ecosystems and agricultural ecosystems. Then, after we go beyond ice caps and groundwater, which were 77% or almost 78% and 22%, now all the other surface water components, some of the other places where we might interact with water and think about water existing, are actually extremely small components of the total water. So you can see lakes is only 0.3%, soil moisture 0.17 or around 0.2%. The atmosphere, 0.03%, rivers, 0.003%, the water that's in living organisms, 0.002%. And also you can see that all those other places have a much shorter what's called residence time. So water that enters those places is likely to not stick around there for a long period of time. It will enter the atmosphere and then it will be moved from the atmosphere. It will fall as rain somewhere and then it'll be re-evaporated. So there's a lot of quick movement between those different, what are sometimes called reservoirs of fresh water. So of course, from a soil science perspective, we're kind of interested in the soil moisture component and then the groundwater component. But of course, things like what's going on in atmospheres and rivers and lakes influence the soil available water as well. So when we think about this watershed scale. Okay, so the second section, or maybe it's the first section of the chapter, kind of talks about thinking about the available water that's in a watershed and thinking about it from kind of a quantitative standpoint or a measurable standpoint. So first of all, let's make sure everybody knows what a watershed is. Sometimes these might be called catchments. And basically these are the areas that are drained to a common point. So if you think about if you're standing on a certain place along like a river or stream and you're looking uphill and thinking about all the land where water might have fallen as a raindrop and then might have flowed downhill and ended up kind of flowing to a certain place where you're standing. So that could be huge if you're standing someplace like the bottom of the Mississippi River. That watershed drains a huge portion of the United States. Or a watershed can be small if you're standing high up on a mountain peak and you just have a small area, maybe an acre or less, that's draining to a certain point. But the watershed concept is not necessarily something that indicates what size you're looking at, but kind of indicates the shape of the landscape and how water would be drained. Okay, so that's what a watershed is. And then if we want to think about what might be the fate of water that enters a certain watershed, and again, that might be a small watershed or a big watershed, we can think of, first of all, P, the first part of our equation here, as being the incoming water. So water normally comes into a watershed from the sky. Now, of course, we have a lot of manipulation of water these days, so we might actually be pumping water in, channeling water in from a different area and using it as irrigation and whatnot. But in the natural setting, the water is going to be coming from the atmosphere as precipitation. That may be rain or snow. And then it has three potential kind of outcomes, places that it can go from there. One, it can be lost as ET, which stands for evapotranspiration. So that is a combination of evaporation, the transfer of soil, water, liquid particles on the soil surface, and then they're evaporated back into the atmosphere, in transpiration, which is the movement of liquid water, transforming it into gas, a gaseous form of water vapor, but through plants. So that's ET. It's one thing that can happen. The second thing that can happen is SS, the water can be stored in the soil. Okay, so that's probably something that you're interested in, capturing water. If you live certainly in the West, you're interested in having good soil storage. If you live in another place, you might be actually interested in minimizing your soil storage because maybe there's too much water for what you're trying to grow. And then the third component is discharge. You could also think of that as like runoff. So this would be water that moves off the landscape, maybe flows into a stream, into some sort of canal or river, and then flows out of the watershed over the surface, but does not remain in the watershed anymore. So these are the three potential fates that water coming into a watershed can have. And we want to kind of go through each of these in a little bit more detail to have a greater understanding of how, different kinds of management impacts can change whether water is going to be lost to evapotranspiration, stored in the soil, or lost as discharge or runoff. Okay, so kind of within the evapotranspiration component, there's another term that I had listed on the last page that I kind of skipped over, which is called interception. And we did mention this in the last lecture as well. Interception is basically the idea that sometimes water doesn't even get down to the ground at all, but it lands on a tree branch or even a blade of grass, and it ends up landing on the plant and then returning often to the atmosphere without ever having any contact with the soil at all. And so that amount of water is called the intercepted component of water. And some environments have very high interception, some would have much lower interception. Coniferous forests, where there's a lot of persistent leaf vegetation, right? Needles throughout the whole year, they don't lose their needles in the winter. May have only 30 to 50% of the water actually ever making it down to the soil at all. A huge percentage, half of the water may just stay up in the leaves and then re-evaporate into the atmosphere, never interacting with the soil. And this is especially true in these coniferous environments that get a lot of snow, because, right, the snow lands on the leaves, it's more sticky than water, and then it might persist there for a long period of time, not really making it down to the ground, and then it might kind of melt and then just re-evaporate right back into the atmosphere. So this interception is kind of a special case, but kind of goes within the component of the evapotranspiration part of our equation here. And then when we think more about evapotranspiration more broadly, there's a few different kinds of things that are going to affect how big the evapotranspiration component is. So the first thing is the type and extent of vegetation. So like the types of vegetation and then how much vegetation there is. So remember, evapotranspiration is two pieces: evaporation right from the soil surface, but also transpiration, loss of water as water moves through plants. It's absorbed by plant roots, moves through plant internal systems. There's xylem systems if you've taken plant biology or biology, and then is evaporated through their stomates or their pores out into the atmosphere. And certain kinds of vegetation just do this better than others, and certain kinds of vegetation are a little bit more conservative with their water. But certainly the more vegetation you have, the more plants are pumping water from the ground into the atmosphere. Plants are very effective pumps. Many plants require to be constantly pumping, otherwise they wilt, they get limp, and they fall over. And so the more vegetation you have, the more evapotranspiration is going to be going on. So that's one piece. Another piece is climate of the region, and in particular humidity, so how much moisture is already in the air. So areas that are really humid already have a lot of water vapor evaporated into the atmosphere, whereas low humidity areas are pretty dry. They don't have a lot of water in the atmosphere. And basically the areas that are dry, that are lacking water in the atmosphere, are essentially very thirsty. The air has a really high capacity to evaporate any moisture that shows up very, very quickly. Whereas areas that are very humid are already close to their capacity to hold moisture, so they don't actually pull water out of plants as fast as areas that are very dry, right? So like if you have a puddle in kind of a humid Florida climate, or you have a puddle out in Las Vegas in the summer, that puddle in Las Vegas is going to disappear very quickly. Your puddle in Florida is going to disappear much more slowly. Or your wet t-shirt in Vegas in the summer is going to dry super fast. Your wet t-shirt in Florida in the summer is not going to dry as fast. So there's kind of a climate component as well. So if we kind of combine these two things, we can look at this map of the United States, and this is showing the estimated fraction of precipitation that's lost to evapotranspiration, combining data from 3 decades in the United States, okay? And so the areas that are shown in red, oranges, and yellows have a very high percentage of any water that comes into that watershed being sucked up and lost to evapotranspiration. So that means there's going to be very limited discharge and very limited soil storage, the two other potential fates. And in some cases, the areas that are in orange and red actually have a higher evaporative loss than new precipitation that's coming in. So they must have water that's maybe being pumped in from other areas that's being irrigation-based water that's pumped up from groundwater or from other watersheds that's being dumped on these surfaces, that's being lost to the atmosphere, that's in excess of the amount of new water that's actually falling in that watershed in any certain year. Okay, then as we move into the green areas, these areas have high evaporation. So these are kind of dry prairie land areas. And then blue areas are having much lower, so I shouldn't necessarily say much lower evaporation, but a lower percentage of the total water that comes in that's lost to evaporation. So they have much more water left over for discharge in rivers and soil storage. And then as we get down to the areas that are like in purples and pinks, we have a very low percentage of the new precipitation that's coming in that's lost to evaporation. So these areas probably have a climate that's not as conducive to evaporating, probably a colder climate. Colder areas don't evaporate as well. We already said humid climates don't evaporate as well. So places like Seattle or like Maine are relatively cool and relatively humid. And so even though they do have a lot of vegetation there, there's enough new rain coming in, the atmosphere is not that good at evaporating water that does show up, so there's going to be a lot of water left over to flow in rivers and streams and a lot of water left over for soil storage. Okay, that's of course very different than places like Southern and Central California. Okay, so there's another concept that's called the soil water deficit. And this is kind of related to what percentage of the new water that comes into a watershed is going to be lost as evapotranspiration. And so the soil water deficit is the PET minus ET. So we already know what ET is. That's evapotranspiration, how much water is actually lost to the atmosphere from the soil surface through evaporation and transpiration. And then PET is potential evapotranspiration, the amount that the atmosphere could evaporate if there was unlimited water around. So there's many environments, again, like Las Vegas or like Plumas County in the summer, where the air is relatively hot, relatively dry, and it has the capacity to probably evaporate a lot more moisture than it actually does, because there's just not much moisture there to evaporate. So in those cases, the potential evapotranspiration is going to be a lot higher than the actual rate of evapotranspiration. Okay, whereas in a wetter area, in a cooler area, the potential to evaporate water might be pretty close to the actual amount of water that's being evaporated, because there's plenty of water there and the atmosphere doesn't run out of water to keep evaporating. So when these two terms are close, there should be plenty of water there. Okay, when these two terms are far apart, when the potential evaporation far exceeds the evapotranspiration, then you will have a high soil water deficit, which means that you're likely to have a lot of potential plant stress. So again, if you live in Las Vegas in the summer, your potential evapotranspiration is going to be a lot higher than your evapotranspiration. So if you're trying to plant a tomato plant out there, you should expect that if you don't work really hard to keep that plant watered, it's going to experience a lot of plant stress. So this is kind of a metric or a way that we can measure and communicate or compare different potential plant stress and potential need for irrigation. So we could have these metrics reported throughout the summer, and as potential evapotranspiration got higher, we would know that we would need to be paying closer attention to potential agricultural ecosystems to go in and give them extra water. So we also mentioned that evapotranspiration is not something that is just about climate, although that has a big impact. It's also about different kinds of vegetation, which behave differently. So this is a diagram that is seen in the textbook, and it shows different types of vegetation. So first of all, native forest, then native grasslands like prairie lands, tree plantations, soybean, and then a wheat-soybean mix. And then this is showing the different amount of total water that comes into the ecosystem, so the precipitation component, and then it's showing whether it ends up as a runoff. Does it flow out in streams and rivers? Does it, in white, drain deep down into the groundwater? So that's kind of part of the soil storage component, but that deep water, groundwater component. Then how much is intercepted by vegetation? How much is evaporated, and then how much is transpired. So these different percentages are stacked in the order that they're written in on the right. So runoff is at the top, transpiration is at the bottom, and you can see there's really a lot of difference depending on what you're growing. So if you're growing trees, you're losing a lot more to transpiration. 67 to 69, close to 70% or 2/3 of your water is being lost to a transpiration. That's even before you add the evaporative component and the intercepted component. Okay, so your runoff is probably going to be less. Your groundwater storage is probably going to be less. And then in these other crops, soybean and wheat, or these other native grasslands, you're going to have less evaporation and less transpiration, probably more evaporation, but much more deep drainage, soil storage in the terms of groundwater, and then also more available runoff. Okay, and this also might vary a little bit, even if you're growing different kinds of plants in an agricultural ecosystem. Whether you're choosing to grow annuals or perennials might have an impact. Usually perennials are going to have a little bit more water demand, like orchard crops are going to have a bigger water demand than annual crops. So anyway, these are all kinds of considerations that you might make when you're thinking about your available water and how you want to use it efficiently. So maybe I should have shown this slide earlier, but here's kind of an image of this transpiration process, this way that water is pumped from the soil through plants and then eventually moves out into the atmosphere. And you can see that next to all the places in the plant diagram here, there's a number, and that number represents a soil water potential, which is what we talked about in the last lecture. And remember, we said water always moves to the area of the lowest water potential. And so you can see here that the lowest water potential is in the atmosphere. So water is being pulled by this kind of essentially vacuum towards the water. Okay, so it's moving from the soil where it might be slightly negative into the roots where it's more negative. And remember, the solutes, things like the salts and stuff that are concentrated in the root tips, pull the water in. Then the water is pulled up kind of by these pressure vacuum systems up into the leaves, and then ends up out in the atmosphere. And as I already said, this is a constant process and ends up using a lot of water from the soil system. So the more plants we have, the more water we're going to be using as this constant pump is working in the ecosystem. Of course, not all plants are the same. We already said that when we compared like trees to grass or other kinds of wheat or soybean crops. But then also within different kinds of crops, there's very different water use efficiencies. So we can think about how much dry mass of plant is produced per water loss to ET. That would be something's water use efficiency, because right, water lost through a plant is transpiration. That's something's water use efficiency. And we can also compare, this is a slightly different scale, but we can compare these different kinds of plants, and we can see that certain plants need a whole lot more water to be produced than other plants. So things like cabbage, squash, lettuce, potatoes, tomatoes, these have a pretty low water demand. And then other crops have a much higher water demand. Apples that are grown on trees, right? They need more water. And then certain kinds of crops that are, of course, adapted to grow in much wetter ecosystems like sugarcane and rice demand a lot of water. So they're not very from a water use perspective, not very efficient crops to grow. And then things like corn has a relatively higher water use demand as well. So anyway, we can think about how we want to use our water by kind of choosing which kinds of crops we might be interested in growing. Evaporation from the soil surface is a different component than the transpiration, the water loss that's actually going through the plant that we've been talking about so far. But areas where there's lots of transpiration, there's probably also going to be lots of evaporation because the air is going to be kind of in demand for water. It's going to be hot and dry. And so in arid areas, we might have as much as 50% of precipitation lost as evaporation from the soil surface. That number is not important, but just thinking about the fact that there can be a lot of water loss in that way. So some things that we can do to try to reduce that water loss is keep our soil covered. So these are many of the same kinds of techniques that we might want to do to kind of manage our soil, to maintain soil aggregates, to maintain good organic matter and organisms in the soil. But we might kind of mulch our soil, keep it covered, not as exposed to the sun rays. And so that might be by having different kinds of cover crops or mowed over dead cover crops, keeping the soil armored. We might intentionally add extra kinds of mulches to the soil. Some people do this on a kind of a garden setting or composts on top of their soil to kind of keep the actual soil separated from the atmosphere. And then in many places, you also see people doing this with plastic. So that could have a kind of potentially pollutant negative impact on your soil, but it is a way to kind of keep water separated from the atmosphere. So if you had some sort of drip irrigation system going on, you could put plastic over the top of that, and then the water that was dripping onto the soil would really be stored in the soil. Some of it's going to be, of course, soaked up by the plant and transpired into the atmosphere, but you might not be losing as much water through straight up evaporation off the soil surface. And this is some strawberries with this mulch. You see this a lot. The mulch also might be serving a purpose to kind of heat up the soil faster. It's kind of like a little mini greenhouse over your soil. But one of the motivations for doing this might be to reduce water loss as well. So you may have seen this as you've been driving around places like the Central Valley. Okay, so all that discussion so far is kind of helped us understand what are some of the things that influence that first part of the equation, the soil storage, the evapotranspiration. The second part of the equation is soil storage, how much water is going to be stored in the soil. And so there's also things that are going to affect this. And we talked a lot about, soil structure and soil texture, having the capability to infiltrate soil in the first place is going to have a big impact on whether that water is going to get down into the soil. And basically the potential for the soil to hold water, we learned last time, it can be related to its field capacity, right? The field capacity is how much water the soil can hold after gravity kind of drains some of the water away. And so we learned that that depends on soil texture, and then, the movement of water through kind of a capillary movement around in the soil, grabbing onto the soil matrix, grabbing onto soil solutes. That's going to impact how high that field capacity could be. On the other end, or on the other hand, as some water drains out of the soil due to gravity, that component that's called gravitational water that we talked about last time is usually going to end up in discharge. Some of it might be stored down deep in groundwater, but much of that's going to probably drain down into a stream or a pond or be lost as runoff from the watershed. Okay. And then if we want to think about then within the soil profile, where the soil might be storing water, we should remember that there are kind of two areas. There's the vadose zone, which we said is the area that's above the water table. That's the unsaturated zone. And then there's the saturated zone, the area that's kind of below where we find groundwater. Okay, so a lot of the easily plant available water soil moisture component is up in this vadose zone where this kind of capillary movement of water might be moving around. And if we want to be getting water off the soil surface down into the soil, either in the vadose zone or in the groundwater zone below the water table, we need to think about all the sort of soil structure properties that we've already talked about before. So we want to minimize compaction. We know when soil is compacted, there's not enough macropores to kind of infiltrate water into the soil. We know we want to maintain good organic matter. Where we have organic matter, we're going to have better aggregation of soil particles to maintain better macropores for better infiltration. We also talked about things like clay or things like calcium and other polyvalent cations being good promoters of aggregation. We also mentioned that a good best management practice in soil is to maintain cover. And so when we have cover, we have a disconnect between the raindrops hitting the soil surface. And we learned that when rain hits the soil surface, it breaks apart surface aggregates and kind of creates a crust on the surface of the soil that prevents water from infiltrating. And so we want to maintain cover so that we have water landing on little blades of grass or other kinds of mulches or cover crops. And so then the water will drain down or run down that vegetation and hit the soil much more slowly and have a better opportunity to end up being stored inside the soil. Another thing that we have mentioned before, but is also important to understand, is that, of course, the intensity of the rainfall, the way that the rain comes in, or the way that the precipitation more broadly comes in, is going to have a big impact on whether that water ends up being stored in the soil or not. So as we've already mentioned, where we have a lot of intense rain coming very quickly, that might quickly overwhelm the ability of the soil to infiltrate water. And so that water might end up as discharge instead of soil storage, right? Surface runoff instead of soil storage. And this is basically what happens when we have a flash flood. We might have a high intensity of rain falling over a wide area of a watershed all at once. And we might then also have soil that for whatever reason doesn't have a very high capacity to absorb water in the first place, to infiltrate water in the first place. And so then we have a whole bunch of surface water moving across the watershed and then maybe draining into some sort of river or stream. And so the stream will shoot up really quickly, really fast. And I'll link to some videos of some flash floods to show you on the canvas or on Canvas. But anyway, that's basically what happens when we have a flash flood. The ability for soil to store water diminishes, and then all of a sudden we have that other part of the equation, the discharge component, go up really quickly. Another place where we have kind of a lot of potential flooding and flash flood implications are in urban areas. So flash floods sometimes happen in like desert areas where there's limited ability for the soil to store water. And then when we do have an intense rainstorm, a bunch of water runs across a desert, it creates a flash flood. But the same kind of phenomenon can happen in urban areas as well. So basically, as we cover up soil surfaces and pave areas to make roads, to make sidewalks, to make driveways, to build homes, we get rid of our macropores, we get rid of the ability of the ground to absorb the water. And so we replace what were previously pervious surfaces, areas that water could kind of infiltrate, with what are called impervious surfaces, areas like cement that water can't really get down and drain into. And when this happens, then we are, of course, cutting off that soil storage component of our equation and then bumping up our discharge component of the equation and getting a lot of runoff really quickly. So this diagram below shows time on the bottom, so the passage of time during a storm. And then on the vertical axis, it's showing stream discharge, so like how much water is flowing in a stream. And then you can see the precipitation event is shown early on. So it rains for a number of hours, rains a little bit, then a lot more, then a lot more, then a little bit less, and then it stops. And as it's raining, more and more water would be flowing into a stream, okay? And before the storm, there would be just base flow, the base amount of water that's flowing in that stream based on just background drainage from the landscape, groundwater infiltration from the landscape. And then the stream would start to pick up its discharge. And in a non-urban area, that rate at which the water would be picking up in streams would be relatively slow, and it would hit a lower peak because a lot of that water would end up being infiltrated, absorbed, and stored in the soil. So that purple line is a flatter curve. Okay, we're talking a lot about flattening the curve recently. And then in the blue line, we're showing in an urbanized area. So where we have lots of impervious surfaces, it starts raining, the water doesn't have anywhere to go, it quickly drains off cement, through storm drains, ends up in streams, and we get a really rapid and a really high peak of runoff in our streams. So these streams can rise up really, really quickly and do much more damage in these urban areas than in these rural areas. So that's kind of something to consider as we're managing our landscapes as well. Okay, so we mentioned the vadose zone already, the zone close to the surface where soil might be stored, that might be available to plants. But of course, a large area where soil is going to be stored is below the water table, down in the groundwater area. So the water that's underground in saturated environments, not soil moisture, below the water table. So those are terms that we've already gone over. There's a diagram on the bottom left to help you visualize this. You can see where the water table is. You can see above the unsaturated zone, that's a soil moisture. We've already called that the vadose zone. Below that is the groundwater zone. Water is stored in between the soil particles, in between the aggregates, and then also lower down might be actually stored in rock, in cracks and fractures in the rock. Okay, so in areas where there's pretty good pore spaces in between the soil, so pretty good opportunity for the soil to kind of hold a good amount of water, and there's a decent amount of water there, we can call those areas aquifer. So if you've heard of an aquifer before, this is this kind of underground amount of water that might be available. If we want to drill a well into it, we can pump some of it up. It might even be available to some plants if their roots are going down deep enough to tap into the aquifer, even without pumping. And these aquifers take long times to build up. It takes many years, thousands of years for water to kind of drain down over time and end up being stored in these big aquifers. And some of the water is lost every year, some of it just through drainage. That aquifer just might be draining downhill and end up in a river somewhere, some sort of surface water downhill somewhere. Some of it might be pulled up by plants that have roots that are deep enough that they're tapping into the aquifer. And then of course, a lot of that water can be lost if we drill wells and pump water out for use in our homes or use in our agricultural systems. And then that's how we can lose water from our aquifers. We can recharge, or we can return water to our aquifers over time. It's not something that can be done quickly, but if we let water kind of naturally sit on the surface above where an aquifer exists, and we don't quickly channelize it and move it off the landscape for use somewhere else, then water will have an opportunity to infiltrate into the soil, then percolate down through the soil and replenish that aquifer over time. So sometimes in places where we know that we have aquifers that are getting depleted, where we've been pumping a lot of water out of them, there are specific efforts to take water, maybe after it's been cleaned in some sort of water treatment plant, and kind of position it over the aquifer with hopes that that water will kind of drain down and re-enter the aquifer to replenish or recharge that aquifer over time. Unfortunately, this isn't really something that's scalable. So many of our aquifers that are being quickly depleted by lots of well use, a lot of pumping use, are really not being actively recharged at the rate that would be required to sustain them. And so we know that we're using our aquifers up much faster than they're being recharged. And so at some point in the future, and that future may not be very far ahead of us, maybe a decade or number of decades ahead of us, we may not actually have access to the same amount of groundwater that we have been depending on in the last half century to water a lot of our crops and supply a lot of our homes. So this is a concern that a lot of water managers have. So when we want to think about how deep down the groundwater is, it's really hard to actually pinpoint, because first of all, it's something that is going to vary a lot even throughout the year. So right now, you might not have to dig down very deep underneath the soil to hit water, but in August or September, you might have to dig a lot deeper. So the water table might actually be changing in the same place from season to season. But it also just depends a lot on the soil, a lot on the climate, a lot on the vegetation. So we might have some areas where the water table is up near the surface all year long, some sort of swampy area where there's almost always standing water near the surface, has a water table of 0 feet. The water is all the way at the surface. In more humid areas where there's consistent rain, we might have a water table that's a few feet to a few meters or more down in the soil. And then in arid areas, we might have really, really deep groundwater. So in the Central Valley, many people, especially in periods of drought, have to drill down hundreds of feet to be able to hit a consistent groundwater source. So that could be hundreds of meters. I know, at least I've heard of people drilling wells that are like 400 feet or deeper down to try to get water in parts of the Central Valley. So that's a deep, deep, long way to go. So that's where the water is. That water that gets all the way down into these groundwater aquifer systems tends to stay there longer than just the water that's moving around closer to the soil surface. That soil moisture, that betostone water, is going to be pulled by plants or lost by evaporation much more quickly, but the groundwater might stick around for hundreds of thousands of years. And then, as we said on the last slide, what's sort of unfortunate about that is that if we pump water very quickly from these aquifers at an unsustainable rate, we are going to have a really hard time rebuilding that aquifer system or recharging that aquifer system, because it takes a long time for those systems to be recharged, hundreds or thousands of years, which are probably like not really, of course, on the time scale that's going to be very helpful to us. When kind of coming back to our water equation, our P precipitation equals ET plus SS plus D, or the incoming water to a watershed can end up as evapotranspiration, as soil storage, or as discharge. I just want to acknowledge that whether groundwater is considered soil storage or discharge kind of depends on the watershed and depends on the context. So a lot of groundwater, especially of that groundwater or that water table is closer to the surface, would really be considered in the soil storage component. But in some cases, once water drains all the way down into an aquifer, it might be kind of draining downhill into a river system and be lost as a river farther downstream, or it might be pretty inaccessible to a surface ecosystem. So again, it's kind of a judgment call based on the specifics of a location, but getting water down into the groundwater can either be considered soil storage, or in some cases can be considered in that discharge component. Okay, so thinking about groundwater management in California, we have a lot of groundwater that's stored under our state. That's good news, because we don't have a lot of surface water. We're a pretty dry area. We have a lot of agriculture in California that requires a lot of water to be maintained. And so we have been pumping lots of water for many, many decades from these aquifers to use in surface irrigation to support our way of life. So both water our lawns, fuel our showers. I'm on a well at my house. Many of you guys are probably on wells at your house too. And then of course to grow all these different kinds of crops and orchards and animal agriculture, other things like that. And one of the things that we've seen over time is that as this water is being pumped, the ground is subsiding. So what that means is the surface of the ground is actually sinking as the water is being pumped out of the ground. So you can kind of think about if you were standing on the surface of a waterbed and then somebody stuck a straw into the waterbed and started sucking the water up out of the waterbed would sink, and you standing on the waterbed would sink along with it. That's subsidence. So on the left here, I have one of these really famous California agricultural photographs, which is this man. You can imagine he's about 6 feet tall. This is in the San Joaquin Valley, Southern Central Valley in California. And what this is showing on this power line is up at the sign where it says 1925 was ground level in this location in 1925. 1955, due to the advent of wells and pumping, had dropped considerably, okay, 20 plus feet. And then from 1955 to 1977, where the man is standing when this photograph is taken, the ground sunk that much more. And then depending on where you are in California, it's probably sunk as much as another 50 feet since that time. So our whole center of our state is literally sinking, collapsing down into the ground as we are pulling water out of it. And that might not be a big concern to you. It might be if you're in a place like the Delta and you're sinking down below sea level and getting more saltwater intrusion because of this, that might be a big concern. If you live in somewhere like Bakersfield, you might not care a lot about how high the ground is. But this is just an indication about how our aquifers are being depleted. And also, unfortunately, when we take the water out, a lot of times the soil particles kind of collapse down into each other and become more compacted beneath the ground. And so the next time it rains, or the next time there's a flood and water has an opportunity to percolate down to that level of the soil, there may not actually be as much space down in that aquifer location to store water in the future. So we may never be able to kind of recapture that amount of water storage in the ground in the future, which might be a problem if we've been depending on that to water our crops, et cetera, et cetera. So on the middle and on the right are images of two other kind of research studies that are looking at groundwater and aquifer loss. So first of all, in the middle is a picture of California, and this was showing the loss of water from aquifers, like the sinking of surface of the aquifers each year. And so it's showing in California about 70 millimeters per year, about 7 centimeters per year. And again, that might not be shocking on a one-year basis, but if you add that up over decades, that's really losing a lot of water from this underground system. And then on the right is another study that was showing what's called the Ogallala Aquifer, or the High Plains Aquifer, which is in the kind of central, south central part of our country. And it's showing areas in blue that have actually had increases and more water coming into the aquifers. But then most of this big aquifer that's under this part of the country has been declining significantly. So the water level changed from 1980 to 1995. So this is a little bit out of date. The picture is unfortunately worse now than it was then. But in that 15-year period, there is losses of up to 40. I don't know if this is inches or centimeters. Oh, in feet. Oh my gosh. More than 40 feet in these dark red areas in a 15-year period. So these are areas that are being very aggressively pumped to use for different kinds of surface agricultural or surface communities. And there's a lot of concern that we are running out of this water fast, and we have built all our infrastructure around the expectation that this water is there. And unfortunately, that will not be true in the future because we are using it at an unsustainable rate. So anyway, this is something that a lot of people have concern about. Traditionally, we've had a lot of management and regulation around surface water use, but very little management and regulation around groundwater use. And so it's kind of a free-for-all where people can just drill down and pump as much water out of the ground as they can. In California, we did pass a law that's called the Sustainable Groundwater Management Act a few years ago that requires local areas to come up with a groundwater management sustainability plan. So it doesn't dictate what that plan is, but it requires that users in an area come together to make a plan to kind of acknowledge the issue, try to think about what a sustainable use could be, come up with some sort of permitting or regulation system. And so it's kind of a very locally managed thing now in California, and it's just being rolled out. I think by 2025, the first plans need to be in place. So hopefully that's something that will help mitigate this problem in the future. Another interesting thing that can happen in the case of sinkhole or in the case of groundwater pumping is that, especially in places that are built on a rock called limestone, which we don't have a lot of in California, but we do have a lot of in places like the southeast of the United States. When we pump a lot of water out of the ground, we may be actually pumping it out from kind of underground caves. Limestone dissolves away in groundwater to make these openings underneath the ground. And that's not true of a lot of other kinds of rocks. And so when you pump groundwater, you might be pulling water out from these kind of underground caverns or caves. And when the water was in the cave, the water had enough strength to kind of hold up the ground on top of it. But when you pull the water out of the underground cave, and it's now just only filled with air, the air does not have the same strength to hold up the ground on top of it. And so what happens is the surface of the ground can collapse very rapidly down into the space that was previously occupied by groundwater when the pumping happens too aggressively. So these are called sinkholes, and you may have seen some of these bizarre sinkhole phenomenon stories in the news in the past, but basically these are created by shifts in groundwater, and sometimes these shifts might be just natural drainage of water from the landscape, but a lot of times it's exacerbated when we have local groundwater pumping. Okay, so the very last part of our equation in our P equals ET plus SS plus D equation is discharge, which I said we can think of a lot like runoff, like stream runoff, lots from the watershed on the surface. And so we've talked about things that influence evaporation and transpiration. We've talked about things that influence soil storage and groundwater storage. Now we want to talk about some of the things that might influence the discharge from a landscape. And so, as we've already mentioned, the type of vegetation and the extent, the amount of vegetation can have a big impact on whether the water is going to be lost or stored on the landscape. So this is an interesting study that is actually not of agricultural systems, but is in forest systems, and this is kind of relevant to our area. And this was done in the Apache Sitgraves National Forest, which is in northern Arizona. And it is made up of ponderosa pine forest, so very similar to the area around Quincy. And what they did in this kind of famous study that was done several decades ago is they looked at this watershed and they looked at the annual precipitation for several decades. They charted that, so that's what's in the beige columns or tan columns. And then they looked at the runoff in two rivers, the Thomas Creek, North Fork and South Fork rivers, okay, over time. So when there's more precipitation, there's more runoff, right? When more water comes in, more water is getting in the river. That's not surprising. Drier years have less runoff. So that's not surprising. We see that all across the study from 1966 to 1986. But then you can see that in 1978, they went through and they thinned out this 15,000 acre watershed. So they cut a number of the trees. And many of these trees are trees that probably in a more natural fire regime system would have been burnt and probably wouldn't have existed in this landscape anyway. But as with fire suppression, we have ended up with a lot more trees on many of our landscapes, and our landscape is probably really meant to support. And they found that after they cut the trees, not all, but after they thinned the forest and had fewer trees on the landscape, then all of a sudden the runoff started to go up. So the runoff was still tied to precipitation. In years that it was wet, we still had more runoff than in years when it was dry. But in these kind of lower to moderate years after the thinning project, they definitely had more runoff in their streams than they had before. So this is an indication that if we are managing the vegetation on our landscapes in a way to kind of actually lower vegetation or keep it at a more manageable or probably more natural extent, then we're actually not only probably making that ecosystem a little bit healthier and better able to sustain things like fire, but we're also probably increasing the runoff that's coming from these streams, which might have good downstream water use implications. So there's been a lot of interesting work like this in California recently, as we've been struggling, one, thinking about how to manage fires, and two, struggling with thinking about how to manage water. One interesting approach that there's been a lot of research about is thinking about that perhaps thinning our forests has good outcomes for fire safety and fire resilience, but also it might have good impacts for water discharge, water runoff in our river systems that may be able to be used in other parts of California. So this is a newspaper article that was actually written several years ago, but many of these research projects and then management projects are going on now. This quote says, thinning is one of the lower cost options to increase California's water supply and would also reduce the probability of big destructive fires, said Roger Bales, a UC Merced engineering professor who specializes in mountain hydrology. There could be measurable and significant gains, a hypothesized 9% increase in snowmelt runoff if the forests are being thinned. There's about double the biomass in the forest now, Bale says, compared to a century ago. And instead of a few big trees, there's lots and lots of smaller trees. All those extra trees gulp water, right? They transpire water that once would have flowed as discharge down into the Central Valley. These trees are also intercepting more moisture than they would have before, so they prevent snow from hitting the ground and melting into the soil. A lot of that snow gets caught in the tree canopy where it evaporates, right? That's exactly that interception and evapotranspiration component that we're talking about. So hopefully you can see all these three components, the evapotranspiration, the soil storage, and the discharge are very interconnected. And the way that we choose to manage our natural and our urban, suburban, and our agricultural ecosystems all have a lot of implications about how water is stored in a watershed or how it's lost from a watershed. And the more we understand about this, the more control and the more kind of we will be able to improve the outcomes that we want from managing our water. Okay, that's all I have to say about that. Have a nice afternoon, everyone, or morning, or night.